Episode 15, Thrashing and the Art of Memory Balancing. Welcome back. In the previous lesson, we studied page replacement algorithms, a necessary mechanism when physical memory is full. However, this raises a higher-level management question. With multiple processes in the system, how should the operating system divide its precious frames among them? And what happens if this allocation is not reasonable? Today's lesson answers those questions. We will examine frame allocation strategies, explore a dangerous phenomenon called thrashing, and finally conclude our journey into memory management. Part 1. Frame allocation strategies and thrashing. Note 181 to 191.1. The frame allocation problem. The OS must decide how many frames to allocate to each process in a multi-programming system. Each process requires a minimum number of frames, for example, enough to hold the largest instruction. Too few frames lead to high page fault rates and poor performance. Analogy. Think of RAM as a 1,000 square meters plot of land and processes as families building houses. The Land Manager OS must decide how much land to give each family. If a large family gets too little space, chaos follows. 1.2. Frame allocation algorithms equal allocation. With M frames and N processes, each gets MN frames. Proportional allocation. Frames are given according to process size. Larger processes receive more frames. Example, 100 frames, 2 processes, P1 equals 20 pages, P2 equals 80 pages. Equal. 50 each gives unfair, P1 wastes space, P2 suffers. Proportional, P1 gets 20, P2 gets 80 gives more balanced. 1.3. Local versus global replacement. Local replacement. A process may only evict from its own frames. Its performance is isolated but may degrade if it lacks frames. Global replacement. A process may evict pages belonging to others. Overall throughput improves, but one process's performance depends on others. 1.4. Thrashing occurs when a process does not have enough frames to hold its working set, the set of pages actively needed. This leads to constant page faults. The system spends most time swapping pages instead of executing. Classic analogy. A chef's CPU has a small table RAM, but needs 10 ingredients at once. The table holds only 3. The chef keeps running to the fridge disk to swap items, spending more time swapping than cooking. Impact. CPU utilization collapses. The scheduler, seeing idle CPU loads even more processes, worsening, thrashing into a death spiral. Part 2. Controlling thrashing in conclusion. Note 191 to 202.1. The working set model. Thrashing is avoided if each process has enough frames to hold its working set. Definition. At time t, the working set is the set of unique pages referenced in the last delta references. Example, delta equals 10. Recent references. 1,234,125,123 gives working set equals 1, 2, 3, 4, 5. Size equals 5 gives needs at least 5 frames. 2.2. Applying the working set model, the OS tracks working set sizes. A process may only run if the total working set demand is less than or equal to total frames available. Otherwise, it suspends some processes to free resources. Example, RAM equals 100 frames. P1 equals 40, P2 equals 50, gives total equals 90 gives OK. P3 equals 20 gives total equals 110 greater than 100 OS, suspends P1. Freeing 40 gives total equals 70 gives stable. 2.3. Page fault frequency PFF. Control a direct method. Monitor page fault frequency per process. If PFF greater than upper bound gives allocate more frames. PFF less than lower bound gives reclaim frames. Example. Thresholds. Upper equals 0.01, lower equals 0.0001. Game process spikes to 0.05 gives allocate plus 2 frames. Text editor idle at 0.0001 gives reclaim 1 frame. 2.4. Summary of memory management we have covered. Continuous allocation and fragmentation issues. Paging as a modern foundation. Virtual memory breaking physical RAM limits. Page replacement strategies. FIFO. LRU. Clock. Preventing thrashing via working set and PFF methods. Final analogy. Memory management is like a theater director OS. The stage RAM is limited. The backstage disk is vast. The director decides which actors' pages appear on stage. Too many actors cause chaos thrashing. Skilled director balances presence for a smooth performance. This concludes the memory management module. Next, we move to storage management, where we study how the OS manages long-term data storage.